In this question, we were given a function f of x equals x cubed plus 3x squared, and this is a multi-part curve sketching question. I'm showing only a few of the parts at the moment. And the first part says find the critical numbers of the function. The critical numbers are where the derivative is equal to 0 and undefined. So I'll start by calculating the derivative. The derivative would be 3x squared plus 6x. We're looking for when that derivative is equal to 0 and when the derivative is undefined. Because this is a polynomial function, the derivative will be defined for all values, so we only need to find where the derivative is equal to 0. So that gives me the equation 3x squared plus 6x equals 0. I'm going to factor the greatest common factor out, which is 3x, and that leaves me with x plus 2 equals 0. I can set each of these factors equal to 0 to get solutions of 0 and negative 2. So these are my critical numbers. In the next part, it says find the open intervals on which the function is increasing or decreasing. So we're going to build a chart, and we're going to put our critical numbers on the chart. We're going to select test values in each one of those intervals. And we want to test these values into the first derivative because the first derivative is what tells me the increasing and decreasing of our function. So we've got our test points of -3, -1, and 1. We're going to substitute that into the derivative. I like to substitute into the factored form because it's easy for me to tell whether we have a positive or a negative. That's 3 times -3 plus -3 plus 2. This gives me a negative times a negative, which is a positive. So on this interval, we have a positive. On the next one, we have 3 times -1 times -1 plus 2. This is a negative. This portion is negative, and this portion is positive. A negative times a positive will give me a negative on that interval. Then for the last interval, our test point is 1. 3 times 1 times 1 plus 2. That is a positive times a positive, which is a positive. So we have a positive on that last interval. So now we're able to state that on this interval here, our function is increasing, which is from -infinity to -2. And on this interval here, the function is increasing, and that is from 0 to infinity. The interval in the middle, because the derivative came out negative, that interval is decreasing, and that interval is from -2 to 0. The next part says apply the first derivative test to identify the relative extrema. Write any relative extrema as an ordered pair. So we're going to use the chart that we built to find the increasing and decreasing to determine whether we have any relative extrema. The relative extrema would be a relative minimum or a relative maximum. And you can see that we have increasing here and increasing here, and we have decreasing here. So when you have a change from increasing to decreasing, That creates a relative minimum, and that is a maximum. So we know that we're going to have a relative max at that point. And then when you have a change from decreasing to increasing, that creates a minimum at that point, relative min. So the first relative min, we're using the smaller x, which is -2. We're going to have a relative maximum at that point. And since we need to write this as an ordered pair, I need to substitute that -2 into the original function. I'm going to calculate f of -2. That's -2 cubed plus 3 times -2 squared. It's -8 plus 3 times 4. That's -8 plus 12, which is a +4. So the ordered pair -2, 4 is a relative maximum. Then the other value created a relative minimum, and that was at 0. It's a relative min. And I need to know the y-coordinate, so I'll substitute that into the original function. That's 0 squared plus 3, 0 cubed plus 3 times 0 squared, which is 0. So the ordered pair 0, 0 is a relative minimum for this function. As we continue with this question, we now want to find the critical numbers for the second derivative. I've written the first derivative, I've written the original function and the derivative we've already calculated. And now we want to calculate the second derivative. And the second derivative would be 6x plus 6. To find the critical numbers, we would set the second derivative equal to 0 and find where the second derivative is undefined. Since this is a polynomial function, we're not going to get any solutions from the second derivative being undefined. So we'll find our critical numbers by setting the second derivative equal to 0. That gives us the equation 6x plus 6 equals 0. We can subtract 6, and that gives, subtract 6, divide by 6, and we get -1 as our critical number. Then on our next part, we want to find the open intervals on which the graph is concave up or concave down. And we're going to get our concavity from the second derivative. We'll build a chart using the critical number from the second derivative, which is -1. We're going to choose test values in each interval. So I can choose -2 and 0. We want to substitute those test values into the second derivative. So we have our test points of -2 and 0. We'll substitute those into the second derivative. 6 times -2 plus 6, that's -12 plus 6. We're going to get a negative for that interval. And 6 times 0 plus 6 is 0 plus 6, and that is positive. So my plus here looks, my minus looks like a plus. So we have a positive on that interval. So a negative is concave down and a positive is concave up. So on this interval here from -infinity to -1, our function is concave down. And on this interval where the second derivative is positive, our function will be concave up. and that is -1 to infinity. Then we want to find all points of inflection for this function. A point of inflection is a change in concavity, so we're going to use the chart that we already built for the second derivative. And we're looking for a change in concavity. We can see that over this value of -1, we have a change from concave down to concave up. So that's going to give us a point of inflection. We want to write our point of inflection as an ordered pair, so we need to substitute -1 into the original function. That's -1 cubed plus 3 times -1 squared. -1 cubed is -1 plus 3 times +1. -1 plus 3 is +2. So the ordered pair -1, 2 is the point of inflection for this function. In the next part, we want to find any x and y intercepts for our function. So we're going to use the original function to find those x and y intercepts. The original function is f of x equals x cubed plus 3x squared. To find y-intercepts, you let x equal 0, so that's calculating f of 0. 0 cubed plus 3 times 0 squared, that would be 0. So we have an x-intercept of 0. I'm sorry, that's a y-intercept. And then looking for x-intercepts, you're going to let y equal 0. So we're setting our function equal to 0. 0 equals x cubed plus 3x squared. We can solve this by factoring out a common x squared, and that leaves me with x plus 3. I'll set each of these factors equal to 0. And that gives me solutions of x equals 0 and x equals -3. So for my x-intercepts, I have -3 and 0. I'm listing them from smallest to largest, separated by commas. Now we want to use the information from all the parts above to sketch the function. Label the intercepts, relative extrema, and points of inflection. But before I start drawing the graph, I want to combine the information from the chart I made for the first derivative and the chart I made for the second derivative. So for my first derivative, I had critical numbers of -2 and 0. And for my second derivative, I had a critical number of -1. So I'm putting all of those critical numbers on the graph, and we'll notice that to the left of 2, maybe highlight this, on the first derivative to the left of 2, my function was increasing. So from the first derivative, I got positive, which was increasing. And then to the left of -2, for the second derivative, -2 is in this interval here, and so to the left of 2 would be negative. So for the second derivative, we had negative, which indicated concave down. And then I want to look at -1. So on the first derivative, -1 would have been here. So that means that for the value of -1, our first derivative was negative, and that was decreasing. And to the left of -1 in the second derivative is decreasing. So second derivative concave down. Then to the right of -1, but before 0, I can see that for my first derivative, I got negative, which is decreasing. And for the second derivative, I'm now to the right of -1. To the right would be positive, which is concave up. And then to the right of 0, for the first derivative, to the right of 0, I had positive, which was increasing. And to the right of 0 for the second derivative would be in this interval here, which is concave up. So combining these two charts together is going to explain how to draw the curve in each one of the sections. I have, for this first section here, we have increasing and concave down. So I'm going to think about drawing a down-facing parabola that represents concave down, and I want to choose the increasing side of that. And the increasing side of that would be this side here. I'm going to get rid of the decreasing side. So this gives me an example of how I want to draw the curve in this section, increasing and concave down. For the next section, I have the first derivative negative and the second derivative negative, so that's decreasing and concave down. So I'm going to draw a down-facing parabola, and this time choose the decreasing side. The decreasing side would be this side. Let's get rid of the increasing. In the next section, we have the first derivative negative, which is decreasing, and the second derivative positive, which is concave up. I'll draw a concave up parabola, and I want to choose the decreasing side. And the decreasing side is this side here. We get rid of the increasing side. And for our last section, we have the first derivative positive, which is increasing, and the second derivative is positive, which is concave up. So I'll draw an up-facing parabola representing concave up. And I want to choose the increasing side, which is this side here. And that gives me an example of how to draw the curve in that section. So just as a reminder, we got two relative extrema for this function. We had a relative max at the point -2, 4. We had a relative min at the point 0, 0, and we had our point of inflection, which remember is a change in concavity, at the point -1, 2. We also had intercepts that we wanted to include of 0, 0, and -3, 0. We're going to combine all this information to draw the graph. So I'll plot all of these ordered pairs. We have 0, 0, -3, 0, -1, 2, -2, oops, I put that in the wrong spot. -1, 2 would be here. -2, 4 would be here. And those are all the ordered pairs I have. And then I'm going to go section by section. And I want to draw the portion of the graph that's to the left of -2 in this manner here, which would be increasing and concave down. So that's this section of the graph. I'll draw this portion of the curve increasing and curve concave down. And then in the next section, which goes from -2 to -1, I want to draw that section as decreasing and concave down. And in the next section, which is from -1 to 0, I want to draw that as decreasing concave up. So along this section here, I'll draw the curve decreasing, but now curved up or concave up. And then finally, I want to draw the last section from 0 to infinity as increasing and concave up. So we now have sketched the curve. I'm going to label my intercepts. I'm going to label my relative max of -2, 4, and my point of inflection as -1, 2. So we have our min, our max, our point of inflection, and this is an x-intercept. For this question, we want to solve the problem using calculus techniques. We're going to show the work on our scratch paper for full credit. The monthly revenue is achieved by selling X baseball gloves is figured to be R of X equals 70X minus 0.5X squared. The monthly cost of selling X baseball gloves is figured to be C of X equals 10X plus 1,000. Profit is given as profit is R of X minus C of X. That's revenue minus cost. What is the profit? So we're going to create a function that represents profit, and we have the formula here that it is revenue minus cost. So we're going to do profit, revenue minus cost. Revenue is 70X minus 0.5X squared minus cost. We want to put parentheses around the cost function, so we subtract the whole thing. That's 70X minus 0.5X squared minus 10X minus 1,000. And I'll combine like terms and also write these terms in descending order. It's a negative 0.5X squared. We'll do 70X combined with minus 10X to get 60X minus 1,000. So this function represents the profit function. P of X is negative 0.5X squared plus 60X minus 1,000. And then on the next part, we want to know how many baseball gloves must the company sell to maximize profit. So the maximum will be found using our calculus techniques. We're going to look for the relative maximum, since we're trying to maximize profit. I'm going to calculate the derivative to find the critical numbers. The critical numbers are where our relative extrema could occur. If I calculate the derivative, that will give me negative 0.5 times 2x plus 60. And negative 0.5 times 2 is negative 1. So our derivative of the profit function is negative x plus 60. We're going to find the critical numbers by setting that derivative equal to 0. That gives me x equals 60. So this is a possible value of our relative maximum. At this point, we don't know if it's a maximum yet. So I'm going to calculate the second derivative. And the second derivative is negative 1. So because our second derivative came out to be negative, we know the function is concave down. And because our value of 60 is a critical number, remember the first derivative is 0, so that the first derivative being 0 meant that we have a horizontal tangent line at that 60. So we have a horizontal tangent line and concave down at 60, and that means that we have a relative max. So we need to sell 60 gloves to get a maximum profit. And what is that maximum profit? We're going to substitute 60 into the profit function. So into the profit function, we substitute 60. That's negative 0.5 times 60 squared plus 60 times 60 minus 1,000. Negative 0.5 times 60 squared. 60 squared is 3,600. 60 times 60 is 3,600. Half of 3,600 would be 1,800, and that's negative. Negative 1,800 plus 3,600 is 1,800 minus 1,000 would give me $800. So we're going to get a maximum profit of $800 when we sell 60 baseball gloves. Thank you for checking out my videos. Have a great day.